2 by 2, just to keep things simple. But hopefully it'll get the idea across for you. Is we'll do this. What do you think for 1 second here? All right. Yeah, just put a 1. And all right, let's do this. Here's our system. Okay. So remember when we wanted to solve a system with a matrix, what did we do? We wrote down an augmented matrix, right? We wrote down this. All right. We wrote down this augmented matrix with the coefficients from the system of equations, like so. Okay. And I went through, we could go through and row reduce this and solve, and we would find that this has, I think the way I wrote this down, there should be a unique solution, and that's good. In fact, maybe we should find that really quick. I'll do this sort of quickly, just so I know what the solution is. You know, I could add +3 times the first row to the second row. I would get 0, 1, and 12. And then I'm kind of purposely doing this part quickly. And then I would do -4 times the second row to the first row. I would get 1, 0. -4 times 12 is -48. Plus 4 is -44. So I think this is my solution here. It's -44 and 12. So let's remember that. -44 and 12. What I want to show you now is let's pick this apart a little bit. Let's abstract and repackage this in terms of matrix operations and matrix equations. So remember that this column represents x, and this column represents y, and this bar represents equals, right? Okay, I'm going to write down a matrix for you. And another matrix, like so. So here's a matrix, here's another matrix. What happens if I multiply these two matrices together? So this multiplication is defined because this is 2 columns and 2 rows. So I could multiply this. What happens when I multiply this out? What do you get? Well, let's see, I'll get this row times this is 1x plus 4y, so it's x plus 4y. And -3x minus 11y. Oh, wait. Does that look familiar? Do these look familiar? Well, they should, because they're the left-hand sides of these equations. Oh, so maybe I can represent these equations by a matrix multiplication where I take the coefficient matrix. I just take the coefficients from these variables and put them in the matrix, which is what we did up here. And then I have this other column vector matrix whose entries are my variables. Yeah. And if I multiply those together, I get sort of my equations back. I'm missing the equals, but I have the left-hand sides back. So maybe if I had written this instead, so that was 4, 0. If I had written this, then if I were to carry out this multiplication, and keeping in mind this equal sign, I would get exactly these equations back. I would get exactly these equations back. So what this suggests is that this system of equations situation can actually be represented by a matrix equation. So maybe if I call this matrix A, and this matrix X, and this matrix B, I have exactly this equation that we kind of solved before. AX equals B. Cool. So I can capture this whole essence of system of equations in a matrix equation like this very succinctly. AX equals B. A carries all the coefficients of the variables, X is the variables, and B are the things, are the constants to the right of the equal sign. And notice to solve this, we just solved this a second ago. What did I get? I got X equals A inverse B. So what you might do X equals A inverse B. So what you might do is you should probably check that A inverse B equals the solution to this system of equations that we got. So that's negative 44 and 12. Remember, this is A, this is X, and this is B. What I would say you should do is find the inverse of this matrix and then multiply it with this B, and you should get negative 44, 12. So we now have sort of another way to think of solving a system of equations. Instead of row reducing in the first place, we could just sort of think of it as row reducing instead to find an inverse and multiplying by this result. And it should give us a solution. Okay. So that's sort of to tie everything together. You know, this is like why we're doing this. We've sort of generalized and abstracted and made up all these matrix operations. Why? Well, it turns out now I can neatly package something that we did last chapter in a sort of new language, a new context, which is kind of nice. You know, we like to do that in math a lot for whatever reason. So I don't know. Maybe you guys aren't as impressed, but anyways, I'd be remiss not to tell you about this. So there we go. That's one reason why we're doing what we're doing. Okay, so I'm out of things to say now about 6.2. So looking ahead, next week we'll start in 6.3, which will be sort of applications to economics. We're gonna have an economic model that we work on where we'll solve problems in economics using matrices and matrix equations. And later on in chapter 8, matrices will make a comeback in probability. So you guys studied a little bit of probability in D116. In chapter 8, we're gonna use matrices to solve probability problems that you could not solve before. Something called a Markov chain. So we'll see what all that's about in chapter 8 in a few weeks. Anyway, does anyone have any questions? I am done talking. So if there are no questions, then we will spend the rest of today working on activities. I can put you guys into your breakout rooms. And we'll spend the rest of the time working on activities. So there's the 6.1b and 6.2a that would be good to work on. That 6.1b is due tonight. And I believe 6.2a I said was tomorrow. So you may want to work on those. I'll put you guys in your rooms now, and then we'll just spend the rest of the class doing that. All right, here we go.